Okay, good morning. So hang on, we need this. Let's try and get this guy. Right, good. Right, so your mechanics revision continues. I will have a session now and another session tomorrow morning. I can promise you at the outset there won't be anything as exciting as Elon Musk's rockets landing. The lectures will be quite mundane. All I'm doing is taking you through a tour through the material we covered last term, picking out what I think are the most important points. But of course, there will be some topics I won't cover, and there's no excuse for not going back and looking through the lecture material in more detail. There are hard copies of what I'm going to talk through either side here, and these are also posted on the usual place. Okay, so today we will be talking about angular momentum and spend a lot of time reviewing the essentials of central forces, gravitation and orbits. Tomorrow then will be spent looking at moments of inertia and Lagrangian mechanics. Okay, so without any further ado, let me remind you of the definitions, and when we're talking about orbital motion, it's very convenient to work in polars with r and theta. So we begin by reminding you that one can write the velocity vector v in terms of these quantities. So just to remind you where this comes from, we have, so if I write the position vector in terms of Cartesian, so that's I cos theta plus j sine theta, so this is the radial unit vector in terms of the Cartesian unit vectors. Let us then write r, the actual vector itself, as and we have perpendicular to this another vector which is theta hat. I'm just writing here the expressions which are on the slide. So that is, if you resolve this, you can see this is minus I sine theta plus j cosine theta. Okay, so that's, and then r itself, so the position vector then is, of course, nothing more than r the scalar I cosine theta plus j sine theta. Now coming to the couple of lines which aren't on the slide, I want to just remind you how you go from this position vector to the velocity vector, okay? So we have r dot. Firstly, I differentiate the scalar quantity r, I beg your pardon, so that becomes r dot I cosine theta plus j sine theta. But then we have to also account for the variation in time of theta, and so this is going to give us a r minus theta dot sine theta I plus theta dot cosine theta j. Okay. I and j themselves are not moving in this problem, so we don't have to worry about the differential of those. But if we then look at this and compare to the expressions we have for the unit vectors r hat and theta hat, we see this is nothing more than r dot r hat plus r theta dot theta hat. Okay, so that is a reminder of where this velocity vector comes from when written in plane polars. And you can differentiate it again, so it expands once more, and then you get an expression for the acceleration, which you can write in these terms. Okay. Angular momentum is, of course, something which is central to this discussion. We have this definition, J equals R cross P. So remember, very importantly, angular momentum, it's a vector, so it has a direction, and it has a direction which is perpendicular to both R and P. Okay, so if R and P are in the plane of the slide here, plane of the screen, then J will be perpendicular to those. Okay. So if you have angular momentum, we know from linear mechanics that when we have momentum, what's very important is to think about what rate of change of momentum is. That gives us a link to Newton's second law. So of course, if we have angular momentum, we should immediately ask what is the rate of change of angular momentum. So starting from this definition, and it is a definition, we ask what is the rate of change of this. Okay, so let us evaluate that. So firstly, R cross rate of change of momentum, dp by dt, and then differentiating the R, dr by dt cross p. Okay, we squint at that for a little bit. We say, aha, dp by dt, we know what that is, that's just force. Then we look at this term, and because p is in the same direction as R, then this disappears. This is 0. So we end up with R cross force, and that is, and this is, we define as torque. Okay. So this is one of the, these are two of the key relations which you really should remember and have at your fingertips, that torque is the R cross F, and that is the same thing as the rate of change of angular momentum. And this is, of course, very analogous to the Newton's second law expressed for linear motion, that F equals dp by dt. Okay. Okay, so now we move on to what we are pretty much solely focused on, which is the question of central forces, which are this very, very important special case in nature. And I've gone on 2 slides here. Let's go back one. Okay, so a central force, that is a force which acts just towards the origin. Okay, so here's the origin. Here's a radial vector going out to the body which is experiencing the force, and the force acts along this line. Okay, so that's what defines it, and it flows from that whatever the nature of this force, it should also just be a function of r. It shouldn't depend on theta. Okay, so in nature we have several very obvious examples of this, one being gravity, there we are, depending on 1 over r squared, and also the Coulomb force, once more, of 1 over r squared dependence, both pointing in the r direction. Okay, so what consequences does this radial force have? So we've defined torque. Let us therefore think what sort of torque such a force would exert in this case. So R cross F, F is of course just radial, so if we do R cross something which is radial, it will vanish. So a central force can exert no torque. If that is the case, because torque is equal to the rate of change of angular momentum, then the rate of change of angular momentum is 0. Okay, so we have this very, very important consequence that for a central force, the angular momentum will be a constant of motion. Okay, so that is something you've known for a long time, but this is the argument from which it flows. Okay, so let us think, because we're going to be using angular momentum a lot. Therefore, for a central force, how can we write angular momentum? Very obvious, but let's just go through it. So J equals R cross P, which is R cross mv, which is R cross m. And now let me write V in terms of that expression we derived at the top of the board. R dot R hat plus R theta dot theta hat. Okay. Now, I'm taking a cross product of R with R hat. That will clearly vanish, and we'll only be left with the second term. So we get m R squared theta dot, and we've taken a cross product, so what we end up with must be a vector. So this is the magnitude, this is the direction, let me call it n hat. What is n hat? Well, n hat is a unit vector which must be perpendicular both to r and to theta hat. N hat is r hat cross theta hat. Okay. So the value of the angular momentum is m squared theta dot, and its direction is perpendicular to both r and theta. So if they are in the plane of this slide, J is pointing out of the plane of this slide. And J, to emphasize again, is a constant of the motion. So if I have a particle which is starting to move in this plane and J is conserved, what consequences will there be? Well, we start with angular momentum which is perpendicular to r and v. This angular momentum is constant. This means that any point in the subsequent motion, it is also perpendicular to r and v. So the dot product of j with r and the dot product of j with v will be 0 in both cases. This means that the motion this particle undergoes must start and remain in this plane. So motion under a central force lies in a plane. Okay, then one of the things which we spent time looking at in our Hillary lectures was how, for a central force, we can derive Kepler's laws. So you will, looking back, you will find full proofs, in particular for Kepler's third law, which is maybe the most involved to do. Here, though, let me just remind you of the second law and how we get to that. So let us consider the special case of planetary motion. So F is gmn over r squared. Angular momentum must be conserved, so m squared theta dot is conserved. Okay, so if we consider some small interval of time, this planet, let's call it a planet, will move some distance, and it will sweep out some area, what we can call dA, as it revolves through an angle d theta. Okay. So we can ask ourselves, well, what is this area dA? Through geometry, we can presumably evaluate this. So we have so this is a triangle. Now, if you're just remind you of a slight subtlety in this argument and the wonders of calculus. The way this triangle is drawn, you might argue it's split into two triangles, a big triangle and a small triangle. the radius of the big triangle I write as r. There's this difference here. Let me actually put the planet revolving in the opposite direction. So over this period of time, r increases from r to r plus dr, and so the total area of this triangle is going to be a half r squared delta theta, and that would be this triangle here, this right angle triangle, but then you have this triangle up here, and the area of that would be a half delta r times delta theta, okay? But in the limit that d theta and dr and everything tends to 0, dr, etc., tends to 0, then this second order term becomes insignificant, and you're just left with dA equals a half r squared d theta. Okay, so that is just the result of calculus. We can then divide through by dt d theta by dt, or right there, there's a half r squared theta dot. We look at that and we say, aha, I know an expression with theta dot in it, that is j, and so I can write this as j over 2m. And because j is a constant, then dA by dt is a constant. So we have shown Kepler's second law, which is a planet the orbit of the planet will sweep out equal areas in equal times. Something which is incredibly insightful is to think about what the energy of a particle under a central force is. So the energy is clearly given by the sum of the kinetic energy and the potential energy. This you could write down already at school as a half mv squared plus ur, where u is, well, we will specialize soon to the gravitational potential. But let us rewrite v in terms of polars. So this is our expression for v. To get v squared, we dot it with itself, no cross terms, and we get an r dot squared plus r squared theta dot squared. So then this half mv squared then gives us two terms, one depending on r dot, one depending on theta dot. But it's a central force, angular momentum is conserved, and we have this expression for angular momentum. Hence we can take this term and replace it by j squared over 2mr squared. So you see this is a piece of magic where we have taken an expression which was dependent on two coordinates, r and theta, and r dot and theta dot, and we've expressed that in terms of something which just depends on r and its derivative. So we have reduced the problem essentially to a one-dimensional one. Okay. This is just to remind you of something you know. We now let us specialize to the inverse square case of gravity. So therefore, F is equal to minus a over r squared, where a, of course, is given by gmn. And one needs to, because in this expression we've just been looking at, it has this potential energy term, we need to remind ourselves where that potential energy term comes from. So the potential energy is just given by minus r, well, the minus of the derivative of f dot dr, where we go from some reference point to some point of interest, which we define as r. Okay. So the reference point, well, we'll come back to what the reference point is, but we see that certainly in the case of gravity, if you do this integral, you end up retaining the minus sign, and of course the dependence becomes 1 over r. Now we worry about what the limits are. This is there's no such thing as absolute potential. We only talk about changes in potential between a reference point and a point we're interested in. We can choose the reference point to be what we wish it to be, but it's clearly very sensible to choose it to be infinity, because then the constant term will vanish and we are just left with the familiar expression for the potential for gravity. So it goes as 1 over r squared. It has a minus sign, just as the force itself does. Okay, so on to some actual practical problems where we will exercise some of these concepts. So these are a suite of the problems which we did consider, but let us go through them again and remind ourselves of the essential points. So in this case, we take a projectile and we shoot it from the Earth's surface at an angle alpha. This alpha is the alpha between the radius vector and v. We need to get an expression for the subsequent motion, and in particular we're interested in finding the maximum distance it gets to from the Earth's surface. And in this problem, of course, we must make some simplification, so we're going to we'll just assume the Earth is stationary, and also that its radius is a. Okay, so what do we know in this case? Well, the key points we're going to be banking on is that both J, angular momentum, and E are conserved. Okay, so if we can evaluate those at launch, they will remain true for the subsequent trajectory of the particle. So let us evaluate J at launch. So it's just going to be given by P cross V, so R cross P rather. So that gives us MAV sine alpha, because alpha was this defined angle between the direction of launch and the radial vector. Here is our general energy expression, written in terms of J. We can then therefore substitute this value for J in there. Here it is. Okay, so this expression will remain true for all time, whatever the value of R dot is. But there's one particular moment where we know what the energy is, and that's when it is launched. So when the particle is launched, it is at radius r equals a. Though we've gone to great lengths to derive this expression where the kinetic energy is split into two terms here, still when we know it was launched, it had a velocity v, which was at an angle. So that velocity, the kinetic energy associated with this velocity is just a half mv squared. So just to be clear, so the kinetic energy at launch is a half mv squared. You knew that, but this could be split into an r dot and a azimuthal component, but we don't need to do that. So we know that the total energy at launch is a half mv squared minus g big M little m a. So that's the E at launch. Okay, so that is the simple expression you would have written down if you hadn't even started doing this course. But that is, because energy is conserved, we can equate that to this more general expression which will apply for all the subsequent motion. So this is what we do in this line here. Remember, what we're being asked to do is to find what is the maximum height. Okay, so here's the particle is shot up, and it eventually reaches a maximum height before it comes down. So at this point here, r dot is equal to 0. So this defines r max. When it's at its maximum radius from the Earth, it is no longer travelling away from the Earth. Its radial velocity has gone to 0, and that means we can set r dot to 0. Okay. This then gives us this expression which turns into a quadratic, which we can solve for r max. No need to actually do that in real time. It's a quadratic, so it has another root. The other root corresponds, of course, to r min, another place on the orbit where it is not going any further away or any closer to the Earth. Okay, so maybe a point here where it comes in, and this would be r min. Of course, it may actually, as on this picture, it may well strike the Earth before it could actually reach r min, but that doesn't remove from the correctness of the equation. Something else we can read into this, and one could get asked, it's interesting to say, well, what about this r max? It's going to be some finite value, but let's consider the case where r max is at infinity. What does that mean? Well, when r max is at infinity, it means that the rocket has actually achieved escape velocity. The Earth's gravitational field is no longer applying to it. Okay, we continue and travel out of the solar system into distant space. So, looking at this expression, can we actually see where this applies? Well, if you look at this, well, if r max is infinity, then the right-hand side of this expression must vanish, and from this we get this relation here, and we see that we can get some condition on what the actual velocity is, and this, of course, is the escape velocity. So in this case, the escape velocity, so from 1 with r max goes to infinity, we see that v, which is the escape velocity, is equal to 2g big M over a. Interestingly, it has no dependence on alpha. This escape velocity, if I'd asked you to work out the escape velocity at the start of the question, you would have probably said, well, I know how to do that. I would just equate potential energy. So this is just a check. So if I work out change in PE going from r equals a to infinity, what is that change in potential energy? Well, it's just essentially just this expression where I put r equal to a. Okay, so the change is just big G, big M, little m over a. Okay, so this is I'm writing change. I'm just interested in the magnitude of this quantity. Then I can equate this to a change in kinetic energy. So if I start the object with a certain velocity, a certain kinetic energy, by the time it gets to infinity, all that kinetic energy will have disappeared and it will be turned into potential energy. So I write a half mv squared. This defines the escape velocity. And again, from solving this, you see that the escape velocity is 2g big M over the square root of 2g big M over a, which is what we got from this exercise earlier. Now, we've been talking about this energy equation. What I want to do now is to remind you of this very elegant concept of effective potential. Okay, so this just comes from the fact that we have, by making use of the conservation of angular momentum, we've replaced this azimuthal kinetic energy term by something which just depends on J and R. And now what I will do is subsume this together with U into a general effective potential. Okay, so it's a cheat. This isn't really a potential energy, but in the problem we can write it as such. So this is how effective potential is defined. And now this looks very much like, as I said earlier, a one-dimensional energy expression. And this enables us to get insight into many problems without actually solving the radial equation. So one thing we can say right away is if we take this equation and rearrange it so that we just have the radial kinetic energy term on the left-hand side, because this is a square, then we know that this always has to be greater than or equal to 0. Let's say it always has to be positive. And this means that for allowed motion, therefore, we conclude that the total energy must always be greater than the effective potential. So if we draw any plot or graph of effective potential, we know that always the total energy being greater than the potential energy, the effective potential energy, defines the allowed region of motion. So for the case which will interest us most often, the effective, in the inverse square law, so UF for inverse square law, it's drawn on the slide, but let us just recreate it here. So it has these two components. Firstly, we have the just the gravitational component. So this is the minus big G, big M, little m over R. That's how this varies. But then added onto this, there's the J squared over 2mR squared. So this is positive, and it's varying more quickly because of the R squared. So this goes down like this. So this is the J squared over 2mR squared. So if we add these together, we get our total effective potential here. Okay. So let me just draw that again and come back to this point that the allowed motion is where the effective potential is less than the total energy of the system. Okay, so if we're talking about motion under inverse square law, there is this case where, here's the generic line here, so this is E, so this is the total energy of the system, this is R, so the allowed motion is underneath here. So we see that R can vary between this point, a minimum radius, and that point. So there is an orbital motion going on where the radius is varying. So this, of course, must be the special case of elliptical motion. Okay. So R varies between R min and R max. Then you have this other case where, well, what about, let's say that the orbit has less energy. Let's say it just has energy here. So in that case, the radius because the allowed motion is everywhere underneath this line, and the line is just touching the bottom of the curve. So the radius is not varying, and this is, of course, a circular motion. So the radius is fixed, and what it's interesting to see is the total energy is actually less than that of the elliptical case. And finally, we have the case where you could be up here, and then there's only, so everything is allowed underneath this line, but the energy only crosses the line at one point, and this is the unbounded orbit. And it turned out to be a hyperbolic orbit. Okay? So these are the three cases one should have in mind. Okay. All this can be expressed also in terms of this equation for an ellipse, which involves E, which is this is the general equation for any conic orbit. So the three special cases exist here depending on the value E takes. Now we did actually derive this expression, and it was a lot of fun, but that derivation is off syllabus, so don't worry about, I mean, it's good if you can do it, but you won't be expected to do it. But the point here is to remind you that expressions from orbits can be expressed in this formalism also. And so the three special cases we've spoken of have E, this eccentricity parameter set to 0, that is the circular motion. If it's between 0 and 1, you get the elliptical case, and if it's greater than 1, you get the hyperbolic case. And with some manipulation, you can get useful expressions in terms of this eccentricity parameter E, and also the semi-major axis A of the orbit for things such as the minimum distance of approach, the maximum distance of approach, and the total energy of this orbit. Okay, so this is the total energy of the orbit written in terms of E. It is it's more than a couple of lines of working to show that is the case, so you're not supposed to intuitively see that this is so, but we did prove that to be the case in the lecture. Okay, so I would imagine if you're in any exam, if you were given questions expressed in this formalism, you're likely to be given the expressions you need, but what you should know is what E represents. Okay, so another few problems. I think we're going to work through three of them here. So firstly, let's put a satellite into a geostationary orbit. So a geostationary orbit is an orbit where you put a satellite above the equator. It's a circular orbit, and it has a period of 1 day. It has a period of 24 hours, such that it's always above the same point on the equator. And this is very useful for communication, for example. So firstly, you're asked to calculate what the radius is, and you're told the radius. You're asked to calculate the velocity. So this is kindergarten mechanics, circular motion. You just set the central force to the centripetal force. This gives us an expression which relates V and R. We know what the period is. That can also be expressed in terms of V and R. You get this expression here, which is a special case of Kepler's third law for circular motion. So this gives you a t squared is proportional to r cubed dependence. But since we know what the radius is, and we know what the period is, that's 24 hours, we can work out what the velocity of this satellite is. 3,080 meters per second. Okay, so this was a rather simple hors d'oeuvre. Now let us we go on to the more interesting part. So the satellite is to be put in a geostationary orbit, but it starts in an elliptical orbit with a perigee at a certain point and an apogee at another point. So the perigee and the apogee, these are also pieces of jargon you should not be intimidated by. So this is in the elliptical orbit. Let's actually just look at the picture. It's easier to describe. So here is an elliptical orbit. So the perigee is when you're the point of closest approach. So this is the perigee. And the apogee is the point when you're furthest away. Perigee, apogee. Simples. Okay, so just to remind what we were asked. So when it is at the apogee, the point furthest away, the rocket is fired to put it into the circular orbit. So we're asked to calculate what change in velocity does the motor need to impart to achieve this feat. Okay. So firstly, this we can the final thing to be said is that for the first thing to be said is that for the final orbit, this is the geostationary orbit, so we know all the properties of this orbit. We've just worked out what the velocity needs to be. So what we should focus on is what are the properties of the elliptical orbit. So for the elliptical orbit, we know while it's still in that orbit that for sure angular momentum is conserved and energy is conserved. So at points A and B, the apogee and the perigee, angular momentum must be the same. So this is an expression of the conservation of angular momentum, okay? NVR equals MVR. MVR at this point equals MVR at this point. Also here, we can calculate the energy because we know at least symbolically what the velocity is. We have it will just have this tangential component. It's not moving away from the Earth, it's just moving tangentially. So its kinetic energy is a half MVA squared. This is its potential energy, and it is equal to the same two quantities here, but with a B subscript. Okay. So this gives us an expression which we can solve for VA in terms of RB and RA. This is just from the energy conservation. Now at this point we can go back and invoke the conservation of angular momentum, and this is going to, no, we've already done that. Here it is. So this information has actually already gone into here. And right. What we have been told what RA and RB are, that's numerical information we had on the previous slide, okay? So here we can actually solve this and we get a numerical result for VA, okay? So this expression, just to recap, has come from conservation of energy and conservation of angular momentum. Tells us what VA is in terms of RA and RB, which are known parameters. So we can work out what VA is, which is the velocity in the elliptical orbit. We know what the velocity should be in the geostationary orbit, and so the difference between those two things is the answer we're going for, and that answer turns out to be 1,280 meters per second. Okay, so example 2. Yes. So this is an example where we start this time a spaceship in a circular orbit, and then at a certain point the spacecraft is given an impulse which we're told does not change the magnitude of its velocity, but it certainly changes the direction of the orbit. Okay, so it starts in this black orbit, and at this point here, it's given a prod such that its direction changes and it's going up here. Okay. But the velocity does not alter. So what's important in this question is that so the energy is the same for the two orbits, but something which has changed is the angular momentum, right? So some rocket boost or some external prod has changed the direction, and so the J is different. Okay. So we're asked to find what is the apogee and perigee of the subsequent elliptical orbit. Okay, so well, the energy equation, because energy is, let me go to this second line first. We know that the energy in this circular orbit is the same as the energy for the subsequent elliptical orbit. So here is the energy written for the circular orbit, half mv0 squared minus alpha r, and this is a generic expression for, well, the energy anywhere in the subsequent elliptical orbit. Okay, it says energy at B, but this is a generic expression for the energy. So this we know. What we would like to know is what is the angular momentum of the final orbit. So it's not. So what we do know is what the velocity is at this point, and we know what angle it is set to move in, right? So we need to write that J is equal to R cross P, which is, if you like, RP sine phi. So if this is R and this is some direction which it goes in, so this is the angle phi. But the angle we are given is not phi, but this angle theta here, okay? So we have to write that J is equal to mv0 r sine phi, which is the same as mv0 r sine pi over 2 minus theta, which is actually mv0 r cosine theta. Okay. So this is the angular momentum of the elliptical orbit. And that will be equal to the angular momentum at any point around the orbit. So this is point A, but a very particular point of the perigee there is mvb/rb. Okay, so we want to find out what the radius of this point is. So we can set r dot to 0 here, because it's at the perigee or apogee, r dot is 0. And so here, so this is the energy expression, the energy of the circular orbit, and this is the energy of the elliptical orbit at point B. On the left-hand side, if we look at this for a bit, we realize that we actually can work out what V0 is, because in a circular orbit, we can equate forces in a circular orbit, and this gives us a relationship between alpha, which is, of course, big G, big M, little m. We can equate that to the centripetal force, and this actually gives us an expression for what V0 is. So putting all this information together will give us a quadratic expression for RB, which is the perigee. Of course, we have another root, and that is the apogee. And so looking at the bottom line, RB is therefore given by big R into 1 plus or minus sine theta. Okay. So I'm going to make one comment and then we'll leave the rest for tomorrow. Having waded through that maths, let's just understand what's happening in terms of the effective potential. So again, let me draw an effective potential case. So we started with, so this is the starting UF has a shape like this. They always have shapes like this, but it was circular motion. So what does this mean? It means we were sitting here. Okay, so this was the energy. So this is circular motion, of course. So the energy of the orbit was such that we were sitting at the bottom of the potential energy well because it was circular motion. So we have a new orbit. The energy has not changed, but in the new orbit the angular momentum is different. And because UF depends on the angular momentum, this means the shape must have changed. So what has happened, so this is the new orbit, so it has a new value for J, so a new value for the shape of UF. But what hasn't changed is the total energy. So now we have, so this is the perigee and apogee. The energy has not changed, okay? So we've gone from one shape for UF where we were previously sitting at the bottom to a new shape for UF where we are now intersecting with the energy at 2 points. Okay, good. So tomorrow I'm going to cover a little more quickly another couple of examples, and then we'll move rapidly on to moments of inertia and Lagrangian mechanics. So I'll see you tomorrow at 10 o'clock. You're supposed to do this, are you? Yeah, I know, it's a misery, isn't it, working in a bank area?